Okay, so let's continue. Let's continue today with Chapter 5. Chapter 5 talk a lot about what are fuels, how is electricity generated, what are the positive and negative consequences of burning carbon-based fuels, and that's a lot part of this chapter, talking about fossil fuels. I'm going to really dig into that a little bit. How much heat is released when fuels are burned? We talk about that. And what are biofuels? We'll talk about that, and we won't get too deep into biofuels, but we will expose you to it, and you will at least be familiar with the concepts and the importance of them. Just by way of review, you should know the combustion triangle. This is important to what we talk about in terms of creating energy, heat energy that runs machines. Know that we need fuel oxidizers and heat, and again we have the fuel and oxidizing heat. This is our reactant side, and we get this product. When it's complete combustion, we get CO2 and water. That's the goal of a good combustion, is CO2 and water. Also note that in a hydrocarbon combustion, the equation is balanced. It balances itself, but for you in class, you have to learn to write the values down. So we have this balanced equation, and this is complete combustion because we see CO2 and water, which is our goal. We also notice that we have energy is the capacity to do work, and the energy we talk a lot about in this chapter is energy that turns machines. It makes machines work, engines. And there are two types of energy. There's potential energy because of the position or the composition, and then there's kinetic energy. When it's at rest, it's potential energy. When it's in motion, it is kinetic energy, and work equals force times the distance you do that work. We know you also have to differentiate between heat and temperature. Heat is the flow of energy from a hotter body to a colder body. Okay, so you're not actually, the cold air isn't cooling you down. You're actually trying to warm up the cold air. Temperature, however, is what you measure with the thermometer, and that is the average kinetic energy. The units that scientists use are joules and calories, and we know that the calories that scientists talk about are different than calories that you talk about in health, and we'll talk about health, I believe, in chapter 9. But they can be interconverted. Calories to joules can be interconverted using a conversion factor that we show you here. 1 calorie equals 4.184 joules. I don't expect you to necessarily memorize that conversion factor. If we need it, I typically give it to you. Okay? I'll try to remember that too when I write the exam. This slide shows you some examples of how that energy looks. So if you raise your calculator, most of you didn't bring an apple, but if you raise your calculator or pick up your cup to drink your coffee, that's about a joule. So you're going to usually you're going to be, for things you do, like for example, you rub your eyes, right? That's about a joule. Heartbeat's about a joule. So you're going to usually be 3 joules and less. With most of the just common things, wave your hand, you're going to be less than 3 joules. So just give you an idea of what that energy looks like. Energy and is basically energy can either be endothermic or exothermic. We talk a lot about exothermic energy when it comes to fuels, because it's basically taking a fuel that has energy contained within its chemical bonds, and they're at a higher energy, and they fall off a cliff to a lower energy and release that energy. And when we write that energy, we write it as a negative value, and we note that depending on the size of the carbon or the number of carbon units and the molecular structure, we get a different amount of energy, and we take advantage of this depending on where the energy is used to turn the machines. Coal's been used a lot, and we use octane in our vehicles, and ethanol as well. Wood is our campfire. So that's what happens. So not all fuels are equal. Yes.
I have a question. So, is there any type of relation when it's going in the opposite way, in a positive way, or would that just not be it?
There is a relationship.
Okay.
The energy needed to do okay. He's asking a question if it's going the opposite, endothermic. Yeah. Endothermic absorbs the energy, and the amount of energy it needs to absorb is proportional to the reactants as well. So yes, the relationship of knowing what those reactions are and the composition and the number of carbons and the units and what they are still holds. That is correct. But here we're just emphasizing exothermic because we're going to be talking about these machines. Okay? Good question. Yes, there is a relationship. So it falls off a cliff. If it goes downhill, that's exothermic. If it has to push its way in the other direction, it's endothermic. And we can interconvert these units. We simply know this unit. This is a standard. We look up on a table. And so we can interconvert these units from kilojoules per mole to just kilojoules per gram. And we can do all types of interconversions. We note again that endothermic absorbs energy, brings the heat energy into the system. Exothermic pushes it out of the system. Endothermic example would be photosynthesis. That's the all-time classic example of endothermic, which is a source of carbon-based life on Earth. It's carbon and oxygen getting together, and voila, we create carbon, hydrogen, oxygen. It's mostly carbon and hydrogen, and we have oxygen, and it comes together. Voila, we get this life form, you, me, and your best friend. Energy, the energy changes at the molecular level. The molecules are vibrating at the molecular level. They have motion, and the energy attacks the molecule at the molecular level and it breaks the bonds. And if it's exothermic, it releases the bond. Okay, does everyone follow? So here we show you examples of different bond energies. I don't expect you to memorize these bond energies, but I really would like for you to note the one on triple bonds of nitrogen. Nitrogen used a lot in explosives, and this is why, because there's a lot of energy there. And in fact, some of the race car, I don't know if they use it in NASCAR and those types, but some of the other racers, they'll use all types of chemical fuel additives. Many of them will have nitrogen species in them because of the bang for the buck in the engine. So, so there we have it. So bond energy is important. So that brings us to where we start to slow down a little bit and look more closely at the rest of Chapter 5. We're starting here on the slide entitled Fossil Fuels and Electricity. And I think this is perhaps slide 14 in this presentation. So we're going to take a look at this diagram. On this diagram, everything you see on this diagram, there's a question that I might ask you about. Absolutely. This diagram you will want to spend time looking at, memorizing the concepts, understanding the concepts, because I ask a lot of questions from this diagram alone. Okay? Let's start, first of all, with the verbiage on the right side, and then we're going to walk through this power plant here. The first law of thermodynamics, energy is neither created nor destroyed, but may be transformed from one form to another, and that's important. In other words, we can't create nor destroy energy. We can't do it to matter either. We can't create nor destroy it, but we can transform it. In other words, you can take the energy in wood and transform it into heat that warms us at the campfire or we make our s'mores with. Or you put it in an old steam engine, right, and you run the locomotive, okay? So it's important that you note that. Can't create it nor destroy it, but you can transform it. That's the energy we have here now has been here, and it's going to be transformed into something else. Second law of thermodynamics, the entropy, randomness, is a key thought for entropy of the universe is increasing. In other words, the randomness, it would really like to be more disordered than ordered. It's really pretty. It takes a lot of energy to hold yourself together, right? So it would rather be on spring break, okay, than to be sitting in an 8:30 science class, okay? Takes a lot more order, you get it? So it's randomness. So that's what's happening. So these molecules would really like to break apart and release that energy. Okay, the potential energy stored within them. That is what they like to do. More atoms, more parts, more randomness, more entropy. Okay, so with those concepts in mind, we're going to talk about this power plant. Okay, and I like to start the power plant with the burner. That's where I like to start the discussion. You can start anywhere you like to, but I'm going to start it at the burner. And here's why. The little yellow lights, this is the fuel. These are fossil fuels. This is a fossil fuel plant, which means that it needs the oil company to send it oil. Send the hydrocarbons to it. Send the coal. So this could be either coal or it could be a liquid fuel, okay, that you get from oil drilling. Okay, so that's where fossil fuels are used. And it's used to boil water. Okay? So you're trying, and so when it gets to you, you have heat coming out of a radiator, coming out of some device, pushing out of a furnace. If you have a home furnace, you have it pushing out of there. Okay? And even there, you're going to have a fuel source, right? You're going to have a gas line in, and you're going to produce gas. But here, this is a huge burner. Okay? All right? So we have this huge Bunsen burner, and it's boiling the water. And here's what happens. So what we have here is the potential energy in the gas, in the fuels, right? It's being combusted, right? And that combustion, we have a fire, right? We have a fire, we have fuel, oxygen, and a heat source. And now we're boiling the water. This water, which is liquid, because we know water has three states of matter, right? Solid, liquid, gas. Here it starts as the liquid, and it's turned into the gas. That's our goal. The goal of this burner is to turn the water into steam as efficiently as possible. That is the goal of that unit. It wants to do it as efficiently as it can. Okay? Yeah. Oh, sorry. No, you're good. I get you now. No problem. That was using a few joules.
Yeah.
Okay. So here we go. So it turns it into steam. The purpose of the steam is to turn the turbine. This is a mechanical device. This is the same thing that happens in Holland with the waterfalls. The water, but instead of steam, it's just natural water that falls and it turns the turbine. This is, in fact, what happens out at the Hoover Dams. Okay? The waterfalls turn the turbine. In this case, we don't have a waterfall. All right? So we use steam to turn the turbine. So this is what you want to do. So this, okay, potential energy, okay, turns into kinetic energy that when it hits the turbine becomes mechanical energy. Okay, does everyone follow? Okay? That mechanical energy turns a generator. And this is where the sparks fly for the electrons, to the 3D structure of electrons moving through the wires that we talked about, I believe, in Chapter 1 or Chapter 2. This is where the 3D electrons start to run around the wires and pass through the building and through some type of resistance, and we get light. This is where it happens. So this is where electricity comes from, folks. It comes from using kinetic energy converted to mechanical energy. That mechanical energy is transferred through the generator, creates the electrons. The electrons start to run down the wires. It lights the entire city, and it completes the cycle. Okay. Does everyone follow? That's how we get it. Now, this steam that's like the waterfall hits the turbine, but it's not consumed. It simply falls off the turbine and passes into a condenser. So it gets condensed here. It's like you're boiling water on your stove. You have your lid on your pot, and the water now is kind of boiling there, and you see it on the lid or it's dripping on the stove. It's condensed. That warm water is sent out to a pond, like the pond on the front of campus at Saginaw Valley State University. That's a cooling pond. The reason the sprayers are there is to help cool it. So this is what's happening here on campus. So that water is going back out to the cooling pond. And so that we can conserve resources, we pump the water right back in here through a pump. Okay? This pump requires what? Electricity, right? Where does it get its electricity from? From the same place it's sending it. You got it? It's going to use electricity here. And it's going to pump the condensed water, another pump, so more electricity, into here, and we burn more fossil fuels, and we do the cycle over and over again so that we can enjoy our lights. A similar process is used in most cases, but there are no cooling ponds because there's not a lot of water. Here's just simple electricity doing it. Okay? Does everyone follow? Be sure you take a look at this. This diagram is at the bottom here. So what we have is potential energy. These are fuel molecules. They're just sitting there doing nothing. We put it in a burner. We combust it. In this case, we get the heat out. We get kinetic energy. That kinetic energy turns to turbine. The turbine converts that. That's by mechanical energy. That mechanical energy is what's used to to crank the generator. If you watch old movies of any type where they would put the crank, that's what they were doing. They were cranking it, giving energy. And they used to be able to sell. They used to sell these model kits. Of course, I'm sure they don't sell them anymore, where you could actually turn this and make your own electricity. Okay, and so then it generates electricity. Some part of this is this entire diagram will be on the exam in some form. This bottom part, I almost always ask a question. In fact, more times than not, I take this exact diagram, I put it on the exam, and you have to fill in the boxes. Okay, that's how it's been on most of my exams. Okay, so you want to pay attention to this particular slide. It's very important. So does everyone get it? We're essentially taking potential energy, converting the kinetic energy to mechanical energy to electric energy. These are the four forms of energy that we see a lot. Potential to kinetic to mechanical to electric. And you want to be familiar with that. Power plant efficiency. As it turns out, we can measure the efficiency of a power plant, but no electric power plant can completely convert one type of energy into another. There are losses at each stage, from here to here, to each step in this process, we lose some energy. And it's calculated by what's called the net efficiency. So it's the electrical energy produced over the heat from the fuel times 100. Some of the energy is transferred into unused heat. So basically, if this boiler is not well insulated, for example, just heat loss to the environment. Some of it just can't boil the water well enough. Heat loss. There's always some losses in the plant here. The loss between the turbine and the generator to this point, there are losses all over the plant. And as it turns out, most power plants, and please note this, it's not on the slides, but I like to ask this question. Most power plants run less than 50%, and I think the number is right about 35. But we'll settle in this class for less than 50%. But I really think the number is right about 35% efficiency. Not good, is it, right? So it takes a lot to send the lights over the Saginaw Valley today. Most power plants run less than 50% efficient.
Okay.
That's a lot of loss of energy somewhere.
So is it the energy putting out or the energy altogether?
Putting out. It puts out only 50% of its potential. So imagine if you could get that up, right? That's fewer plants built, which means fewer resources used, the whole bit. So it takes a lot to really push the lights out. Less than 50%, and again, I believe that number is 35. Okay, it's what it's running at today. But 50% is a good number to keep in mind. But that's okay. Imagine for you guys who do sports, okay, particularly basketball. You don't get to be a starter too long if you're shooting at 35%. Okay, you ain't going to get the ball. You have to do a lot of passing. Okay, all right. That's just the way it is. All right. So that's a lot. That's a lot of loss, and that loss is the best we can do. It's because mechanically we just can't do any better. So there are areas for you, those of you in the future, to figure this thing out. We're running at less than 50%. That's how much weight, that's how much we're losing. That's why I like to do the conservation assignment for you to see just where are we losing, right? And that's what we want to think about. So that's where it is. The higher the temperature of the steam, the more efficient the plant. But what does it's the higher the temperature of the steam, the more efficient the plant. But what does it take to get that higher temperature? We have to do what? Burn more fossil fuels, or burn more fossil fuels that have energy structures with higher energy in their bonds. You get it? So it's kind of somewhat of a which comes first, the chicken or the egg. You get it? All right. So that's what's happening. We want to get that steam. So let's pump the steam. Well, that means we need more fossil fuels. Well, if you need more fossil fuels, we have to dig more oil. Well, we're not going to dig on the land, so we have to dig in the sea. Well, guess what happened? You dig on the sea, you contaminate the dolphins, the whales. Okay? You get it? If you dig on land, we contaminate the land. We'll say, gee, let's go dig where there's no one out there. But someone said Bigfoot's out there. That's a joke. Maybe some of you believe Bigfoot. So I apologize for those of you who believe Bigfoot is real. Okay? Yeah, but you get it? There are consequences, is the point I'm making of it. And that's what we're trying to achieve with the energy. Yeah?
Is that why some power plants are kind of like equidistant by each other?
I'm sorry?
Like, is that why some power plants are equidistant by each other?
Meaning?
For like their energy output, since their energy output is 35 to 50%, or do it not make sense? I don't know.
I'm not sure what the exact question is. See if you can rephrase it for me.
Like, is that why there's not, within counties, there's probably about like 2 power plants within
Versus
1?
versus one. In some cases, that's absolutely why.
Okay.
I get what you're saying. Yeah, where they're located is on purpose, so they can maximize the energy push from the plants. Is that what you're? Yeah, that's exactly why. Okay. Yeah. Later on, we're going to be talking later about nuclear reactors. Not in this chapter. We're going to stick to fossil fuels, but we're going to come back to that very thing when it comes to that. But yes, that's the location of that plant is very, very important, critical to getting the energy push and those types of things. Yeah. By the way, one of the biggest energy consumers in the state of Michigan is Hemlock Semiconductor. Takes a lot of energy to get you your cell phone. Okay? One of the biggest energy consumers in the state of Michigan. So there you have it. We need the power plants. This is the best we can do. This is the efficiency. This is the state of the art. This is not a whine. This is not a complaint. This is the state of the art. So the state of the art is they run less than 50%, probably closer to 35, and that's the best they can do. Now, in the burners today use fuel, some type of fossil fuel. Okay, and we're going to be talking about how we get that fossil fuel. I believe that might be in the next chapter, chapter 6. One of the other sources, of energy is coal. And so on this slide, and I do ask questions about this, you'll want to memorize this slide as well. We have these different forms of coal, okay? And depending on the form of coal, we get more bang for the buck. There's more energy in that form. All right, just taking a look at the verbiage. Coal, an ancient fuel source. Coal is a complex mixture of substances. It is because it basically just comes from the earth, from organics in the earth. Although not a single compound, coal can be approximated as this. Lots of carbons, over 130 carbons, almost 100 hydrogens, oxygens, and you see we have N and S. What happens anytime we have nitrogen and sulfur? If we have nitrogen, we get what? NOx. If we have sulfur, we get SOx, and these are pollutants. So now you understand why coal pollutes. NOx and SOx are pollutants. And so when you see in compounds on N and S, it's pollutant, okay? Higher grades of coal contain more energy. That's just the nature of it. So that's why they're called higher grades. For instance, anthracite has about 35, and so you see all the others here, okay? So depending on which source you use, you get more bang for the buck. I'm just checking to make sure I didn't make a typo. Okay, yeah. So Here we see anthracite has the highest, right? And lignite in this example has the least. So if you're out getting coal, you want to get the one with the most bang for the buck. So let's look at these forms on the left side and the picks for them. Coal is formed from over millions of years of rotten plant materials that accumulate in warm, muddy swamps. And this, with the Virginia mountains, that area is the Virginia mountains and also the Kentucky mountains. That area of the country in the U.S. is just, that environment is just right for coal showing up, okay, over these millions of years. Okay. And they are very proud of their ability, by the way, to produce coal. They were, as the news reports go, they were very unhappy with the Obama administration, who was against coal as it goes. His administration said, we're going to stop coal producing, it's bad for the health. But the people living there said, look, we've lived and died this way for a lot of years, we fed our families this way. And people from the outside were saying, well, you only live to be 50, 60. They say we live a good 50, 60. Okay, and they were okay with that. Now they're happier now with the Trump administration has lifted many of the bans to allow them to go back to mining, so they're happy. So there are always debates about what's good and what's bad, okay? I leave that to society itself. You know, we kind of help all a part of being good and bad in deciding that. But the people are happy back to making coal. But these were the arguments, the NOx and SOx, the pollutants that are produced from it, and what it does to the lungs. Those are the arguments against it. The arguments for it is it's a good source of fuel that's homegrown, and people there get to make the living that they've enjoyed and their grandparents and so on and so forth. Okay, that was somewhat of a political statement. Okay, back to real science. We have coal then. Then we have peat. It's moist, fibrous in nature. Okay? And so these tend to just like flash burn right away. So this is grass, right? Throw a little grass on the fire, a little dry. You get your spark a little bit, so you have to keep throwing it on there. Here you get a little peat, you throw it on, and it lasts for a little bit. Now we start to get into lignite, okay? So now, here it's brown coal found near the Earth's surface. This is a type of coal that the kids would go up in the mountains and just pick up with a bucket and bring home to Ma and Pa, okay? I have a friend from the mountains region, and she said, yep, they go out and they pick up coal when they were kids, and they bring home. And so this is very likely what we're doing. So, bituminous coal is found deeper in the ground. This is where the digging really starts. It's here too, okay? So this is like light digging. And oftentimes when the big manufacturers dig this up, the people who were burning coal in those areas, when coal was used a lot in almost anything in certain areas, they just almost give this away. You can just go up, send the kids up, pick up a pail of coal. And no big deal, because the value was less to them. So it's kind of a cool thing for the families around there, right? They didn't have to buy coal, they just burn this. This is what we're paying for, and this is what we're paying for. This is the first area of the mine, and this is deep mine digging, okay? But with it comes consequences of dust and particles like lungs, okay? And with it comes the side of having NOx and SOx. But it is still a useful form of a fossil fuel. Okay. When we say fossil, by the way, it just basically means you're digging it out of the ground. I guess you guys know that. Okay. So there you have it. This is what coal looks like, and this is how it's valued. Excuse me. In the U.S., wood was used as a major source of energy until the 1960s, when coal became the largest source. Today, 90% of all U.S. coal consumption is due to electric power generation. That's a lot, right? So the coal that's still used is still to generate electricity. And what the plant's running at? Less than 50% efficiency. Okay, Asia-Pacific countries are the largest users of coal worldwide, followed by Africa, Europe, and then the U.S. And the U.S. because of many of the regulations and simply the source of it. But again, the mountainous southeast areas is where coal is found most in the U.S. Drawbacks: mine safety. Environmental harm by mining and it's combustion. So the combustion, so you know why now, the NOx and the SOx. Fly ash that's released, it pollutes the air and we breathe it in. So these toxic things, and the other metals that are there are mercury, lead, and cadmium are really unhealthy. So this diagram just shows you that. I really expect you to know this here, okay, specific area, this order of coal production. I also expect you to at least know some of the side effects. So if I listed the side effects of coal, you should know them. Okay? Crude oil. So we have coal and we have crude oil. And the crude oil is what we use for the burners as well. And so we show you here, well, let's just read through this first, then we'll talk about this. Crude oil is a mixture of several thousand compounds, the majority being hydrocarbons composed of 5 to 12 carbon atoms. This is important to note. That's what a crude oil. So most of 5 to 12, okay, is what the crude oils burn, okay? And gasoline is refined within this to closer to the 8s, all right? So we take crude oil, take a tighter cut, and we get the most of the centered around the 8s for vehicle fuel. Alkanes are hydrocarbons with single bonds between the carbon atoms. Alkenes feature at least one double bond, and alkynes, 3 a triple bond. Yes, I like for you to know that. And alkanes means that it has a single bond. Alkene, E-N-E, has a double bond. Alkyne has a triple bond. That's important to, if you've ever taken a course of chemistry at Saginaw Valley State University. You have to know an alkane, an alkene, and alkyne, even in the 102 general chem level, which is what you're taking. Okay? For 102A, I don't expect you to memorize these prefixes. The one I expect you to know, however, is, I'll tell you the ones I want you to know. Octane, so you can circle octane. So you know octanes, that's fuel, right? And methane and butane for 102A. 102B, yes, all of them. Okay, so you guys, methane, butane, octane. Anyone else? 102B section will learn them all, memorize them all. So here we have methane, which is one carbon. Okay, and note here there's a difference in what's called the boiling point because its volatility here. Okay, it's vapor pressure. Methane has a higher vapor pressure, therefore it boils at a lower temperature. The higher the vapor pressure, which means that the higher it is when it's in a gas state. So methane exerts at same units or same mass exerts a certain amount of pressure, right? And that vapor pressure is very high compared to, say, butane. That's why we have butane in a lighter and not methane. Okay. So we have butane, and then we have octane, which we have in our fuels. Okay? All right? So this is what, so 5 to 12, we don't have 12 on here, but this is what crude oil would look like, and these are the hydrocarbon structures. And these are called linear structures. Linear because they run in a chain. Okay? And that's important to understanding vapor pressure. So note, here's the trend. The higher the carbon count, the higher the boiling point. Note that, write that down. Mm-hmm. The higher the carbon count, the higher the boiling point. So if you have more carbons, your boiling point goes up. It has a higher boiling point. That is a trend I expect you to be familiar with. Higher the boiling point, the higher the carbon count, the higher the boiling point. Okay? So, let's talk then about this thing we call boiling point, because this is important to the next slide you're going to see. The volatility of the liquid refers to is how easy it's transformed into a gaseous phase. How easy does it vaporize? We call that volatility. It is more volatile if it vaporizes easy. easier. Okay? For example, if you pour alcohol on the bathroom sink and you pour water in the bathroom sink, the alcohol will leave faster because it is more volatile than the water. Okay?
So because of its ethyl properties,
I'm sorry?
is it because like alcohol is basically ethyl?
It's ethyl, yeah, it's shorter chain for one, but it has different forces in it than does water. Water and ethanol is not a perfect comparison. It is just really to tell you that the more volatile, it leaves faster. Comparing the two requires a little bit more chemistry than we're going to probably talk about in this class. But we'll mention it here. Okay? Good questions, by the way. We have in hydrocarbon we have only London forces. In the case of the water and ethanol, we have polar forces that are at work in the OH on the alcohol and the HOH in the water. Okay, so we have what's called hydrogen bonding. In the case of these hydrocarbons that we're going to talk about here, we only talk about what's called London forces. It's like marbles banging into each other. That's what London forces are. In the case of water and alcohol, they actually attract to each other. Okay, they can have a little bit of Velcro stick in them. The London forces are like marbles. Okay, so here we have these London forces. They're called intermolecular forces. And depending on the nature of these, it will either be, the nature of the London forces determines its volatility. Okay? The stronger the forces, the higher the boiling point of the liquid. So the stronger the London forces, it boils higher. Okay? So more carbons tend to have more London forces. You get it? Therefore, they tend to boil higher. The boiling point of a liquid is the temperature at which the vapor pressure of the liquid equals the ambient pressure. At sea level, the ambient pressure, the atmospheric pressure, is 1 atm. You'll want to note, well, you know by now if it's bold, you want to memorize them. So here we show you an example here. And they use, this is interesting, you know, I was just talking about, since your discussion, I just thought of this. This diagram is actually not showing hydrocarbons. It's actually showing OH functionals that you were asking about. But here, what they're really trying to help you to understand here is the difference in vapor pressure is what I was using too. So here, this is at when it boils. When it hits this line, it boils. So notice diethyl ether hits this line at a lower temperature than does ethyl alcohol, which is the alcohol, right, that you put on a cut, and water, that you took a shower with last week. Okay? So you got it? So this is what causes boiling point. Now that's important when it comes to fossil fuels, because fossil fuels are distilled to get fractions that we can use. And the more volatile fractions are used for one set of applications, then the high boilers, the lower volatile materials, are used for others. And we are going to show you what that looks like. Let's start with the barrel. Well, let's start with the verbiage, then we'll show you the diagram. Hydrocarbons will have different volatilities and boiling points due to the different strengths of their intermolecular forces. The primary force at work is London forces, but there are a few others. Okay, but London forces are the primary force in oils. That's it. That's what matters. A process known as distillation is used to separate the crude oil into various components. The light ones and the heavier ones. The long carbon chain, the shorter carbon chain. The less volatile, the more volatile. The low vapor pressure, the high vapor pressure. As the temperature of the boiler increases, hydrocarbons with higher boiling points begin to vaporize. Eventually, the vaporized components travel up the distillation tower and are collected. Over 87% of each barrel of oil is used in the transportation and heating. You get it? Now you understand why people watch the oil prices. If you take a barrel of oil, 87% of it's used in transportation or heating. That's why oil is so important. That's a lot, right? The other 17% is used to make products and things of that nature, like plastics. They go into manufacturing in some form, and a big area is plastics. Okay, that's what it's used. So 85% lets me drive my vehicle and enjoy a warm building. So let's look at the barrel then, and show you what that looks like. Then we'll walk you through the refinery. We take a barrel. Okay. By the way, I do ask questions about this barrel, and I'll tell you almost what question I ask in just a minute. Okay. The gasoline is about 19. So if you take a 55-gallon barrel of oil, 19 gallons is gasoline. So almost 20 gallons, right? So anybody drive a small vehicle, 20-gallon tank, 15, 20 gallon? Yeah. You're driving around, every time you drive your car, you're driving around with a 55-gallon drum of oil on your car. You get it? Every time you fill up your car, that's your 55, that's your portion of your 55 gallon. You get good mileage? No, not necessarily, nope. You get good mileage if you have a good engine. Okay? But no, you're using up 55, someone's got to go pump. For you to drive your vehicle, someone's got to go pump a 55 gallon of oil. So think of all the people on campus, right? What's this campus like now? 10,000? So 10,000, okay? So most of us have at least one vehicle, at least a 20-gallon tank. So 10,000, so that's 10,055 barrels of oil. So when you walk outside, each vehicle, you say, there's a barrel of oil going down the road. You get it? Now for me, yeah, that's a barrel and a half, closer to 2. You get it? Okay. All right. Does everyone follow? That's what it takes for us to drive our vehicles. I want to make sure you get it. So how many, you fuel up at least what, maybe once a week? Or do you try to get 2 weeks out of it? Yeah, you usually get 2 weeks out of it. 2 weeks out of it? Okay. See, me, if I get a week, that's a good one for me. Okay? I drive. Okay. It's what I do. All right. I run out of things to do. I get in my vehicle and I drive. Okay. So every 2 weeks, you're using a barrel of oil. Anybody fill up once a week? Every week, you're using a barrel of oil. That's what's called. So you say, they should stop drilling oil. They're going to tell you, stop driving your vehicle, and I will. You get it? I want you to be able to see that. All right. Now, after that, then we have what next? Home diesel. Oh, there's diesel there. Anybody drive a diesel? I thought about it. It's a big truck. Heavy fuel oil. You got jet oil. Okay. And the other products, this 7 gallons, this is where you get the products we need to make plastics and things of that nature. The type of question I like to ask from this, because it's fun for me to ask it, it may not be fun for you guys to answer, and I've already warned it, my sense of humor is really warped. Okay, but I usually ask something like a student has an economy car. Okay, how many barrels of oil did the student consume that week? One, and you better know it's 55 gallon, 1 barrel, right, for that 20-gallon tank. And someone said, well, it was one student said, well, I thought it was only 19. Close enough. Get it? Depending on the pumping that way, maybe you'll get you 20. Does everyone follow? Yep, 1 barrel is 55 gallons, which gives you your tank of gas for an economy car. Economy car is about 20 gallons. Get it? So just to show, because I just want to make sure we emphasize, that's what we're doing. That's what we're consuming. Okay? By the way, this is what this class does. It tells you what you do every day. Okay? This is chemistry and science around us. So here it is. What happens? You pump, you go to the boiler. You take the crude oil. This comes off the ship or off the tank. It goes into the boiler. What's at the bottom of the boiler? Yeah, fuel source, right? How efficient do most of these plants run? Less than 50%. So you're gonna have to. So you have crude oil that you have to refine, and you have to use crude oil to refine it. You get it? That's a lot of oil. So it comes in at the bottom. The heavies stay on the bottom down here. You cook it up, and everything that's light flashes to the top, and they take it out. And these are all the cuts they take out because this is heating it. And occasionally someone say, gee, we need 1 more gallon of gasoline, and say, okay, fire to burn a little hotter. We probably can push a little bit more out, and we get it. Okay? Hang in there, guys. We will complete the entire hour of this one. Yeah. Stretch if you have to, okay? So this is how we get it, and this is what the refinery looks like. The lights come out the top, the heavies go out the bottom. Know that. Higher carbons on the bottom, lower carbons on the top. But it's not just one little plant. This is what it looks like. This is what an oil refinery, and perhaps some of you guys have seen some around. If you go down the Gulf Coast, you just really see it. This is a plant, okay? So there's lots of towers going. There's a lot of refining going. So it takes a lot of energy to run this plant. See all these holding facilities here. So this is what really, so there's a lot of vehicles being serviced off of this. And there are a lot of homes being heated because of these plants. But the efficiency of the burners, once it gets out there, is less than 50%. I don't know the actual plants are running now. I don't know that number. So, what can we do then? How do we improve the efficiency of what we use? Well, we try to take the one source and we try to manipulate it. And we manipulate it by cracking it and isomerizing it, meaning we take this one, we break it into parts to use for other things, or we take it and we combine it to use depending on the application. You get it? So we break it apart to use for some things, or we combine a couple together to do other things with it. In order to meet the large demand of gasoline, the higher boiling fractions are cracked in the smaller ones. So you take the very large 16s and you crack them down to what? 11s and 5s. You get it? So they crack here. You blend this with your 8s and everything else, and you get your fuel source. So you crack them to get it. You need some more 8s, you crack it to get it. Okay? And that's what it's about. Catalytic cracking uses a catalyst to lower the temperature required to split it. Why? If it doesn't, you have to really put more energy. So catalysts are used, and you're about to be introducing catalysts on the next slide or two. Catalysts are used to lower the energy required to transform fossil fuels into useful materials. Okay? We want to transform those fossil fuels into useful materials. We use catalysts. You want to transform into plastics at a lower temperature, lower energy consumption, we use catalysts. You want to crack them to use for fuels, for gasoline, we use catalysts. Catalysts lower the activation energy required for these molecules to be formed. And that's going to be on this slide. Let's tell you that. Then we'll back up to a slide. So that's what catalysts do. So in a catalyst, in a non-catalyzed reaction, you know we have to go uphill, right? We go uphill, we reach its highest transition point. This is where it has the maximum potential energy, and it falls down. This catalyst, however, says, gee, you don't have to push it up the hill as far. We'll take it a lower hill, and you can fall down. This is the energy. The red line on the catalyst slide, this is the energy. Okay? The energy we output's the same, but the energy it takes to get this is less. Does everyone follow that? Does everyone see that diagram? Can visualize that? We go up a higher, we're non-catalyzed, we have to ride a higher hill before we can reach a point to where we start to have useful energy. Here, less to get there. So catalysts lower the activation energy. You will want to know that. An important catalytic process is the Fischer-Tropsch, which is used to produce gasoline for fuel coal. Know that. So what does the catalyst help us do? Catalyst reforming involves the rearrangement of atoms within a molecule, usually starting with linears and producing one or more branches. So occasionally we'll take these materials and we'll take a linear, that means a straight chain, and we will affix another part to it and make a branch. Occasionally you'll break that linear and you'll reattach it to itself. And you do that to affect the volatility. The volatility is what affects the vapor pressure. The vapor pressure lets you know whether it's going to boil light or it's going to boil heavy. If you need more light, occasionally you'll take a long chain, you'll break it off, refix it, and that makes it boil at a lighter temperature, boil at a lower temperature. On the other hand, you want a higher boiler, you take a linear, attach it to the end of another linear, it makes a higher boiler. You get it? These are called isomers. If we have the same number of carbons but a different arrangement, it's called isomers. It's like taking this classroom. We have a fixed number of tables, a fixed number of chairs, a fixed number of students, and we all of a sudden play musical chairs, and everybody gets up and moves around. That would be an isomer. Or we move the chairs to another arrangement. It would be an isomer. Why? Same composition, except that it's been rearranged. That's what isomers do. And we do that to affect the performance and use of the material. Get it? We want the material to perform a different way, we rearrange it. And that's called isomerization, and we make the isomers. One of the useful areas is a branched hydrocarbon known as isooctane used in gasoline additive to prevent engine knock. What it's found is that in the linear, when it's burned, when it's combust to CO2 and water, it produces a little bit of a when it's doing it. To reduce that, you add isooctane, and now you get the same bang, but you don't get the knock. Okay? And that's why we isomerize these. Okay? All right? No one likes to hear knock in the engine. Okay? You don't want to hear it. Even if it's not harmful, you just don't want to hear it. Okay? So we add isooctane to reduce the knock. Know that. That brings us to ethanol. Ethanol is a biofuel. Okay? Renewable fuels derived from biological sources such as trees, grass, and agriculture. Well, if we use biological fuels, what do we have to do? Go get more trees, go get more grass. So is there an environmental impact? Yes. You get it? But what we put into the air is less than what we put in the air on fossil fuels. So again, it gets back to the balance. Ethanol is an alcohol with an OH functional group. Know that ethanol is an alcohol. I think you know, most people kind of know that ethanol is an alcohol. I don't think we'll have much trouble memorizing that one. Okay? To obtain ethanol from corn, a soup of corn kernels and water is made. So you're basically making the precursor to moonshine. Okay? Then enzymes are used, to catalyze the breakdown of starch molecules to make glucose, which is a sugar. So we make the glucose. The last step involves fermentation to convert glucose into ethanol, okay, followed by purification by distillation. You're distilling the moonshine. That's what's happening here, okay, and that's what ethanol. So ethanol fuel. Ethanol can also come from plants, corn starch, but you have to, again, get the biomass. So there are always consequences, and there's always a balance, regardless of what you use. There's balance in fossil fuels, there's a balance in biofuels. Yes?
Oh, I was just going to say, I grew up in Illinois, and Illinois is one of the largest producers of ethanol.
Yeah.
Central and Southern Illinois produce a lot of corn.
Yeah, they absolutely do. And as a matter of fact, farmers are really excited about the possibility of this because they're going to get to produce a lot more corn. The Iowans, and I lived in Iowa for 5 winters. I count Iowa by winters. Trust me, if you lived in Iowa, you know why you count the winters. Okay, but those areas are really happy with this particular area because it gets another product, and a lot of them are going to get subsidies. So it's really kind of a cool thing to be doing. Thanks for sharing that. So oxygen fuels such as ethanol contain a lower amount of energy per amount of burn. Recall the chart we showed you earlier of all the molecules falling off the cliff? Ethanol is after coal, right? Okay, so you don't get the bang for the buck. So therefore, you don't burn it. They haven't developed engines to burn it pure. It's a blend. So it cuts down on the amount of fossil fuel. So you say, boy, every little bit helps, and it really does. Ethanol reduces 1240 kilojoules per mole of energy, and octane 5060. You get it? 5,660 versus 1,240. There's a big difference in it. So there's a blend here that happens. So automobile engines cannot run on ethanol by itself. So gasoline blends are used, often about 10%. But that's a huge move, right? Recall the barrel that you're driving down the road with, right? Okay. So every 2 weeks you're driving with a barrel. Perhaps you get to stretch that to every 3 weeks you get it? A little bit longer if you use the ethanol, and you get to help the local farmers. okay? Biodiesel, where you're not really as much interested in the bang, you want the tug. So many believe this might be a really good place for it to be used. Another important biofuel is biodiesel, which is generated from fats and oil, such as waste cooking oil. So instead of taking your fryers and just pouring it out in the landfill or sneaking and pouring it down the drain or out in the sewer somewhere, okay, or accidentally pouring it out in the woods somewhere next to your home because you have a lot of acreage, yeah, right, accident. Instead of doing that, biofuel. How do we recycle? How do we reuse these? So typically 16 to 20 carbon atoms, right? So you don't get that big bang, but you get the chug. And here's the other thing. Hydrocarbon contain double bonds. Double bonds are called what? Alkenes. You know that because you just had it 15 minutes ago and you memorized it that quickly, right? So these are alkenes, double bonds. But this is an example of what this ester would look like in the biofuels. And they're called esters, okay? And glycerol is a byproduct of biodiesel, which has applications in all types of other areas for use in alcohol and biofuels. So, renewable energies. If you take a look at this diagram, this is 2015. Note here that fossil fuels, 78%, almost 80% is fossil fuels. Of all the renewables is only about 20%, and then nuclear is really small. It's kind of eye-opening, isn't it? Fossil fuels, okay? Our society still runs off fossil fuels. And there are those that say, we need to cut into this, we need to cut into it right away. This will take time because the engines and the designs have been set for fossil fuels. You get it? Which means there's a lot of engineering and redesign that needs to occur. It doesn't mean it can't happen, but there's a lot of work and research that has to go into that. So of these renewables, modern renewables, traditional biomass, okay? And note here, just not much happening. Solar is another area that's happening, but only 20% is going to what's called renewable right at this point.
I can't think of like what it's called. When you go to a gas station and they have like the cheaper gas, it's like E85.
Yeah, that's what this is.
That's what it is.
Ethanol. Yep.
And you have to like keep using it regularly.
Yeah.
Like on the gasoline.
Yep. So most of those will have some type of bio. It's kind of the bio move. And I think some of the pumps maybe even green. They try to label the pumps now green or something. You can tell I don't use it, right? I know about it because I teach the course. I'm the fossil fuel burner. I am. But yeah, I plant trees. I compost. I recycle. Okay. All right. So the key point is the fossil fuels. It's really huge. So here's a really good area for someone like yourselves to make an impact. Okay. And help people like myself to stop being gas guzzlers. Okay. I think we might be really close here. A few more slides. Okay. Let's get through it. Oops. Ethical principles of biofuels. Biofuels development should not be at the expense of people's rights. Everybody has a right to have what they have. Biofuels should be environmentally sustainable. Biofuels should contribute to the net reduction of total greenhouse gases. These are the rules that we're agreeing to work by and live by. Biofuels should develop in accordance to the trade principles for fair rights of people. In other words, don't force it on someone. Don't force it upon a nation. Don't force it upon a government. Don't those types of things. That people should have a right to decide how they deal with these. Costs, benefits, okay? And so we want you to at least be familiar with this. I don't ask in-depth questions about this, but I will ask a philosophical question that I would expect you to be able to answer from this. Not memorize it, but philosophically understand it. Biofuels potential for more natural sources. We kind of talked about that from the trees, but there's what? An impact. How do we gauge it? Direct and indirect changes in the use of the land, right? You don't want to end up destroying land and destroying other habitats trying to do this. Waste products from biofuel production. What are you going to do with that waste product? We have to think through this. how much energy is required to produce the biofuels. If you're burning fossil fuels real heavily to produce the biofuels, then you have to ask yourself what the benefit is, particularly if those fossil fuels are still emitting things into the environment. Guess what, folks? You survived Chapter 5 of my class. Enjoy the rest of your day.